In this section, we're going to be going over the limit of a function. So what we're essentially going to be doing is introducing the idea of motion and change into these problems, and that is using limits. Okay, so let's go ahead and start with an introduction. So let's consider the graph f of x, which is x squared minus 4 over x minus 2. And let's say we want to go ahead and graph it. So before we do that, it's going to be best to actually factor the numerator, because once you factor the numerator using difference of squares, you can see that it will cancel with the x minus 2 in the denominator, and we're going to be left with x plus 2 over 1, so just x plus 2. So the way that we would actually write this is it's equal to x plus 2, except x cannot equal positive 2, because that's what makes the denominator 0, and we can't have that. So that actually means f of 2 is undefined, and there's actually a hole at x equals 2. So let's go ahead and graph this. And we know what the graph f of x equals x plus 2 looks like. That's just going to be a line. So it's going to look something like that, a y-intercept of 2, slope of 1, and a hole, or a removable discontinuity when x equals 2. Okay, so let's say that even though the function is undefined when x equals 2, let's say we want to know what's happening as x gets closer and closer to 2. So if we go from the left and get closer and closer to 2, we come from the right and get closer and closer to 2, it looks like the y value is approaching 4, right? Where that hole is, except the function does not exist at x equals 2, but it looks like it's approaching a value of 4. Okay, so this is where the idea of limits comes into play. So let's go ahead and fill out a table of values, and we're going to converge onto x equals 2 from the left and x equals 2 from the right. So I chose values 1.99, 1.999, 1.9999, getting closer and closer to 2 from the left, and then I also chose values getting closer to 2 from the right. And let's go ahead and plug these values, evaluate them, and plug them into the function. So let's say we want to evaluate f of 1.99. We could go ahead and plug it into this function, or we can plug it into the simplified form, which is x plus 2, and we would end up getting a function value of 3.99. And now if we evaluate f of 1.999, go ahead and plug that in, we would get 3.999. And now f of 1.9999, we get a function value of 3.9999. And now let's go ahead and evaluate these ones on the right. And the way that I'm doing this in my head so quickly is because I'm using the simplified version of the function right up here. And I'm just adding 2. So next one, evaluate f of 2.0001. We get 4.0001. And then I'm just going to fill in these other ones. Okay, so we want to see what are these values, these function values, approaching as x is approaching 2. And it's pretty clear that on both sides of x equals 2, the function is approaching 4, right? It looks like once we get over here, both of those values from the left and from the right for the function values are getting closer and closer to 4. So what we would do here is we would read this, like I have right here, as the limit of f of x equals x squared minus 4 over x minus 2, as x approaches 2 equals 4. And then here is limit notation, which I'm going to introduce formally on the next page. Limit notation, you read this the way that it's written right above it. The limit of that function as x approaches 2, using a little arrow meaning approaches, equals 4. So that means the function values are approaching 4 as the x values are approaching 2. So this is one way to do it, using a table of values to the left and to the right of the number. So let's go ahead and take a look at limit notation, the general definition here. So here we have the limit notation, which we just saw, And this is read as the limit of f of x, which is the function, as x approaches a equals L. So a and L are just numbers here. And like we mentioned before, this means that x gets closer to a, but does not actually equal a. The corresponding function values get closer to the number L. And just like we saw on that previous example too, the function does not actually have to be defined at a in order for the limit to exist as x approaches a. Okay, so what we just did is we found the limit using the table, and let's do a couple more examples with the same method. So what we're going to do to find a limit using the table, we're going to choose values of x that are close to a, but still less than a. And then we're also going to choose values that are close to a, but just a little bit larger than a. So we're going to choose values of x that are to the left and to the right, and getting closer and closer and closer to it. And if the limit from the left side and the limit from the right side are both going towards the same number, then that number that they are approaching will be the answer for the limit. So let's go ahead and see this example. Find the limit of 3x squared as x approaches 4. So we see that x is approaching 4 from the left. We have 3.99, 3.999, 3.9999, and then from the right, 4.0001, 4.001, and 4.01. So we have values very close to 4, but not quite 4. Now we're going to see what are these function values approaching when we plug in our x values that we chose. So what we're going to do, and maybe I'll just kind of write this over here, I'll just show one of them. We're going to evaluate all of these x values that we chose. We're going to plug them in our function, and it's probably going to give us out a pretty messy number here. I think for the first one here we get 47.76 for that one. So that's going to be this value. F of 3.99 is 47.76. So you can do the same thing for all of them. You plug in the x values and evaluate the function. I'm just going to cheat, and I'm going to plug them in right now. Okay, so we have all of these values, these function values now for these x values that we chose, and it's pretty clear that it looks like the values are getting closer and closer to 48, right? When x gets closer and closer to 4. So we can see that f of x is approaching 48 from both the left and the right. So what we would say here for our answer is that the limit of 3x squared as x approaches 4 is going to equal 48. So our answer here is 48. So in fact, for this particular example, this is one where we could actually plug in 4, right? Because it's actually not undefined at x equals 4. You can plug in 3 times 4 squared, and you actually get your answer of 48. So this will not always be the case. We're going to see why going forward, why it works for this one. Hopefully it's pretty obvious that this is a parabola and it's continuous because it's a polynomial. But we'll see, we'll have a more exact definition going forward. Okay, let's take a look at this next one. We have find the limit of sine of x over x as x approaches 0. So this one's a little bit crazier, right? Because we're introducing not only just a trig function in here with sine of x, but it's sine of x divided by x. So for a little bit of assistance, visually, I just put in the graph. So this is actually what the graph of sine of x over x looks like. It's periodic, so it's going to, actually I shouldn't say it's periodic, I should say it's oscillating, just like the normal sine graph oscillates like a wave, but then dividing by x changes it a little bit. So we're going to see what is the function value approaching as x approaches 0. Hopefully we just can see that the function value looks like it's approaching a y value of 1, right? So we should assume that the answer is going to be 1 here, but we could go ahead and plug in our values. So for 0 in the middle, I chose x values negative 0.03, negative 0.02, negative 0.01 from the left, and then 0.01, 0.02, and 0.03 from the right. So let's go ahead and just plug these in. I'm just going to do one example here. And let's first evaluate f of negative 0.03, and we plug that in. That's going to be sine of negative 0.03 over negative 0.03. That gives us a value of 0.99985. So I'm going to go ahead and plop that in right here. And behind the scenes right now, I'm going to fill in all these other ones. Okay, so here are all the other function values with all the other x values plugged in. So we can see that these function values from the left and from the right are both approaching 1. Okay, and just also notice that f of 0 is undefined in this case because sine of 0 over 0 would give us 0 over 0, which is technically indeterminate form, but we'll worry about that later. Okay, so we would give us, this would give us an answer here. It's the limit of sine of x over x as x approaches 0 is going to equal 1. Okay, so maybe you're asking to yourself, how did we choose these x values right here? Well, sometimes they will be given to us, but if you choose your own x values, you can choose technically whatever you want, but you should be very close to whatever middle value you're actually trying to find. So you could have also chose here maybe negative 0.05, negative 0.03, negative 0.002 or something like that. So it really doesn't matter technically what you choose as long as it's getting closer and closer and closer to your middle value. Okay, so that was the first way to find limits, finding limits using tables of values. Now we're going to be finding limits using graphs. Something to keep in mind is that the function value, the y value, f of a, will not always equal the limit of f of x as x approaches a, even if they both exist. So let's see a couple kind of basic examples here. So example 1, this first example, we can see that f of a, the function evaluated at a, equals L, right? That's just going straight up and then straight across to the y-axis. F of a equals L. In this particular case, the limit of f of x as x approaches a also equals L, because as we get closer and closer to it, it looks like the y value is also approaching L. And in fact, right here, this is actually the definition of continuity. When the limit of f of x as x approaches a equals the limit of f of a, that means it's continuous at that point. Okay, let's see another case here. So in this particular case, f of a is undefined because there is a hole. There is a hole right here, and there's no filled in circle anywhere vertically. So f of a is undefined, but it looks like the limit as x approaches a is going to still equal L, right? Because that's where the function is approaching as x approaches a. Right, and in this last example here, we have f of a exists, but it does not equal the limit. So you can see that f of a is all the way up here. So there's a filled in circle, and in this case, the y value is just called f of a. So f of a exists, except it does not equal the limit this time. So the limit as x approaches a is still L, and f of a is not equal to that this time. Okay, so let's see some examples. First one, for a, we want the limit of f of x as x approaches -2. Okay, so we have this graph. You can see that we have a couple issues. We have some holes here. So let's find -2. So as x approaches -2, what is this function value approaching? So it looks like the function value is approaching 5, right? That looks like the y value that it's approaching. Now for b, let's actually evaluate f of negative 2. F of negative 2 is filled in down here, so that is actually a value of 3 for that one. Okay, next let's find the limit as x approaches 4. So here's 4 down here, and limit as x approaches 4. That's going to be a y value of 7. And for f of 4 is the filled in circle. That gives us 2. Okay, so you can see how having a hole kind of can affect these limits and the function values being equal to each other. Okay, next example. This time we have a piecewise function. So the function is going to be equal to 2x minus 4 when x does not equal 3, and then it's going to be equal to negative 5 when x does equal 3. So this is what the graph would look like. The function is the line 2x minus 4 everywhere except x equals 3. That's when it's equal to negative 5. So let's go ahead and find for a here the limit of f of x as x approaches 3. So as x approaches 3, it looks like the function value that it's approaching is 2, and f of 3 is equal to negative 5. So it's equal to negative 5 right down here. We also could have just used the definition of the function up there. Okay, so hopefully pretty simple for that one. And up until this point, we've had to find limits graphically looking something like this, where it says, what is the limit of f of x as x approaches 2? And then for this, we can just go ahead and take a look at what the y values are approaching. Now we're going to be doing something a little bit different. Now we're going to have something that looks like this. So for this particular one, we want to know what's the limit of the function as x approaches negative 2. So this time, if we come from the left and we come from the right, it's different, right? They're not going to the same place. There's that jump discontinuity there. So now let's see what happens when this is the case. This is where one-sided limits actually get introduced. And one-sided limits are exactly kind of what we were just talking about. It's saying what are the y values approaching as the x is approaching a value from either the left side or the right side of a certain value. So that means we're going to have two things. We're going to have a left-hand limit and a right-hand limit. The left-hand limit means we are approaching from the left. The right-hand limit means we're approaching from the right. So here is the notation. The limit of f of x as x approaches a from the left. So notice that little superscript negative, that means from the left. So the limit of f of x as x approaches a from the left equals L is exactly the way I just read it. And then for the right-handed limit, it's the same concept, except there is a plus superscript. So the limit of f of x as x approaches a from the right with a little plus superscript. Okay, so make sure you know those little notations right there. And let's go ahead and see a couple examples here. Consider the graph of this piecewise function f of x, which is x squared plus 1 when x is less than 1. And then it's x plus 3 when x is greater than or equal to 1. So graphing it, it looks like this graph right here. It's a piecewise function. Let's go ahead and evaluate these limits right here. So the first limit is the limit of f of x as x approaches 1 from the left, right? We have the negative superscript. That means we're approaching from the left. So here is 1. We're going to approach it from the left. So we say, what y value does that look like it's approaching? Well, that looks like it's approaching a y value of 2 when x is 1, right? Next, we're going to be approaching 1 from the right. So we go to the right of 1 and we approach it. And it looks like that is approaching a y value of 4. So that is the difference between approaching from the left and approaching from the right. Okay, and we were nice here and we have a nice graph given to us in my notes. So if we were not given the graph in our notes, we would actually have to plug it in, and it's pretty easy. From the left means less than 1, so we would use that first graph, or that first function, and then from the right means greater or equal to 1, so we would use the second function. Now we're going to see how these one-sided limits affect the limit in general. So one-sided limits are going to be used to help us determine if the limit in general exists. And when I say in general, I mean not from the left, not from the right, just the limit as x approaches a. So it's relatively simple. If the limit from the left equals the limit from the right, then that is what the limit in general equals. So you can see in this definition here, this first one that I have, if the limit from the left equals L, and the limit from the right also equals L, then the limit exists, and then it equals L. Okay, and then if we have the limit from the left does not equal the limit from the right, then that means the limit in general does not exist. Okay, so very, very important, pretty easy little definition there. In order for the limit to exist, the limit from the left has to equal the limit from the right. And if they don't, then we say the limit does not exist. And the way that we can write does not exist, we can be a little bit lazy here, and we can write that as DNE, does not exist. Okay, let's see some examples. Let's use this following piecewise graph to answer these questions. First one says the limit of f of x as x approaches -2 from the left, right? We have -2 from the left. So we find -2, and we're approaching it from the left. So notice we go to the left of it, put an arrow going back to the right of it, and we say, okay, where is that going? It looks like that's approaching a y value of 0, right on the x-axis. Now for the next question, let's approach -2 from the right. So from the right, we go back towards it. It looks like that's approaching a y value of -2. And now we're being asked, what is the limit in general? What is the limit of f of x as x approaches -2? Well, since we have the limit from the left and the limit from the right, since these are not equal to each other, 0 does not equal -2, then this limit does not exist. Okay, and then the last question that we have here is just f of -2. So that's saying what is the function value at -2, at x equals -2. That's a function value of -1. It's wherever the filled in circle is. So that's not calculus at all. Okay, so let's go ahead and see another example. Okay, so let's go ahead and take a look at the first one is the limit of f of x as x approaches -3 from the left. So we are approaching from the left of -3. It looks like that is approaching a y value of 2. Now let's approach -3 from the right. That still looks like a y value of 2. And now we are trying to evaluate the limit of f of x as x approaches -3. So this time the limit from the left and the limit from the right are equal. So that equals the same as those. That limit equals 2. Okay, and now let's evaluate f of -3. So at this time f of -3, there is no filled in circle anywhere. So what I like to say is it's undefined rather than does not exist. I usually use does not exist for limits, and then undefined for function values. Okay, and then for e, we have the limit of f of x as x approaches 0. So as x approaches 0, we can see that from the left and from the right, they're going to different y values, right? So this is actually going to be does not exist. Okay, so for one of the last things here is infinity as a limit. So infinity as a limit, what this means is that for one of our answers, for an answer, we can have infinity or negative infinity as an answer to a limit. So for this to happen, let's consider a graph with a vertical asymptote. We know there's a vertical asymptote, a vertical, invisible vertical line at x equals a, if the function approaches negative or positive infinity as x approaches that a value. So these four graphs that are on here are kind of the four main things that can happen at a vertical asymptote from the left and from the right. So let's take a look at this first one right here on the left. So from the left and from the right, as x approaches a, the function values are going towards infinity, right? It is blowing up. So that means from the left, from the right, and the limit in general, everything is infinity. Okay, so pretty easy. And then for the next one here, the second one, and we have the vertical asymptote, and the function is going towards negative infinity from the left and from the right. So from the left, it's equal to negative infinity. From the right, it's equal to negative infinity, which means in general, it's equal to negative infinity. Third one gets a little bit more complicated. You can see that the limit from the left is going towards infinity. The limit from the right is going towards negative infinity. Since those are not equal to each other, the limit in general does not exist. And then similarly for the last one, the limit from the left is negative infinity, limit from the right is positive infinity. Since they're not equal, the limit in general does not exist. Okay, so hopefully that's pretty obvious. Vertical asymptote, you're going to have infinity or negative infinity as one of your answers. So let's go ahead and see this example. Let's find the limit of f of x as x approaches 2 from the left and as x approaches 2 from the right, where f of x is 1 over x minus 2. So we're given a graph for this question, which makes this a lot easier. On the next question, it's going to be very similar, except we will not have a graph. So the limit, let's do the limit from the left. The limit as x approaches 2 from the left of f of x. All we have to do is look at the graph because it's a lot easier than doing it by hand. If we go from the left, it's approaching negative infinity. Now let's do the limit as x approaches 2 from the right. And we look at the graph once again. From the right, it's going to positive infinity. Okay, so that was pretty easy. That's all we had to do. If the question asks for the limit of f of x as x approaches 2, then it would not exist because from the left and from the right are not equal. So let's do one that's a little bit harder. Let's find the limit as x approaches 3 from the left and from the right of g of x, where g of x is 2x over x minus 3. So first, recognize that this is a simplified rational function, which means when the denominator equals 0, whatever x value that gives us will give us a vertical asymptote. So there is a vertical asymptote, put VA, vertical asymptote at x equals 3. So that means if we're approaching from the left or approaching from the right, we're either going to get an answer of negative infinity or infinity. Figuring out which one is which is going to be the difficult part. There is a very quick way to do it if you don't know what the graph looks like, and that is going to be creating a table. Okay, so here's the table. We have the x value of 3, which we know g of 3 is undefined because that's the vertical asymptote when we are dividing by 0. And what we're going to do is we're going to pick a value to the left of 3 that's very close to 3. I'll pick 2.999. And then we're going to pick a value from the right, 3.001 I'll pick. You don't have to pick those exact ones, but it has to be very, very close. And now what we're going to do is we're going to plug in, we're going to evaluate g of 2.999. If the answer is negative, that means the limit from the left, because this is from the left of 3, is negative infinity. And if we plug it in, and we get a positive number, then it's going to be going towards positive infinity. So let's go ahead and see what happens. So g of 2.999 is going to be 2 times 2.999 over 2.999 minus 3. So another shortcut here is we don't actually have to evaluate it. We can just think this in our heads. This answer is going to be negative, right? It's going to be negative because the numerator is positive, but this denominator is negative. Positive divided by a negative is negative. So we know that that's negative. Now let's do g of 3.001, and we plug that in. And hopefully you're kind of looking ahead and seeing what's going to happen here. We plug this in, we get 3 times 3.001 divided by 3.001 minus 3. We know that this answer is going to be positive because the numerator is positive, so is the denominator. So we know that this answer is going to be positive. So you can see that we actually don't even have to find the exact value, which is nice, because now we know that the limit as x approaches 3 from the left, g of x, is negative infinity because the value directly to its left was negative. And then we also know that the limit as x approaches 3 from the right is positive infinity because the fg of 3.001 was positive. Okay, and then like we said before, we knew it had to be negative or positive infinity because there is a vertical asymptote at x equals 3. Okay, so if we happen to know what the graph looks like too, which technically we should, when x is equal to 1, 2, 3, there is a vertical asymptote. We should, kind of off the top of our head, with a little bit of thinking maybe, we should know it looks something like this. Okay, so that's if you remember anything from graphing rational functions. Okay, then once you have the graph, this question becomes a lot easier. Okay, one more question here, and it's nice and easy because we have a graph. We're introducing some trig here. So the limit of tangent as x approaches pi over 2 from the left, and the limit as it approaches pi over 2 from the right. So let's do from the left first. Once again, we should be able to do this without a graph because we should be able to know what tangent looks like. So the limit from the left, where is pi over 2? Pi over 2 is right here. From the left, it's going towards infinity. And now for the limit as it approaches as x approaches pi over 2 from the right, we go to the right of pi over 2 and approach it, and that is approaching negative infinity. Okay, so with the graphs, it's pretty easy. If you don't have the graph, you might have to plug in some values directly to the left and directly to the right using a table of values, or you can try to graph it yourself. Okay, so that is it for this section.